Hello everyone. Welcome back to your maths journey. Let me start with a little puzzle. Have you ever looked at the tiles on your classroom floor or the windows in your house and thought, why do they fit together so neatly? The secret lies in a special four-sided figure called a parallelogram. Now, a quadrilateral is any shape with four sides, four angles, and four vertices. But a parallelogram is unique. Both pairs of its opposite sides are parallel. That simple condition makes it wonderfully symmetrical. And here's the fun part. Draw a diagonal inside it, and suddenly the figure splits into two identical triangles. It's like cutting a sandwich perfectly in half. Both pieces look the same. That's the first of many magical properties we are going to uncover today. So, let's get started. Alright, first big property. Theorem 8.1. A diagonal of a parallelogram divides it into two congruent triangles. Imagine parallelogram ABCD with diagonal AC. The diagonal cuts it into two triangles, triangle ABC and triangle CDA. Now, since side BC is parallel to side AD and diagonal AC is a transversal, angle BC equals angle DAC. Similarly, since side AB is parallel to side DC, angle BAC equals angle DCA. And of course, AC is common to both triangles. So by the angled side angle rule, triangle ABC is congruent to triangle CDA. In plain words, the diagonal works like a mirror line, splitting the parallelogram into two equal halves. Cool, right? It's like folding a paper kite along its diagonal. Both sides overlap perfectly. Now, once we know that diagonal trick, we immediately get another result. Theorem 8.2 says that in a parallelogram, opposite sides are equal. So, AB equals DC and AD equals BC. This follows directly from triangle congruence. Here's the converse, Theorem 8.3. If in a quadrilateral, each pair of opposite sides is equal, then the figure must be a parallelogram. Think of building a rectangular photo frame. If you cut opposite sticks to exactly the same length and fix them together, you automatically get a parallelogram frame. So, side equality is both a property and a test for parallelograms. Pretty handy. Next, let's look at the angles. Theorem 8.4. In a parallelogram, opposite angles are equal. Suppose you open a book halfway. The cover in front makes some angle with the spine, and the back cover makes the exact same angle. They are opposite and equal. And yes, the converse holds too. Theorem 8.5. If each pair of opposite angles of a quadrilateral are equal, then the figure must be a parallelogram. That's because the angle sum of quadrilaterals and parallel line rules force the sides into alignment. So now we've got two tests. Opposite sides equal or opposite angles equal. Either way, the figure locks itself into a parallelogram. Now comes one of the most powerful results. Theorem 8.6. The diagonals of a parallelogram bisect each other. Imagine diagonals AC and BD intersecting at O. You will always find OA equals OC and OB equals OD. Why? Because triangle AOB is congruent to triangle COD and triangle BOC is congruent to triangle DOA. Congruence strikes again. And the converse, Theorem 8.7, is also true. If diagonals of a quadrilateral bisect each other, then it must be a parallelogram. So, the diagonal bisection test is super practical. Even carpenters use it. If two diagonals cut each other exactly at their midpoints, the frame they've made is definitely a parallelogram. Let's test these properties with a real example. Suppose ABCD is a rectangle with angle equal to 90 degrees. We need to show that all angles are right angles. Since side AD is parallel to side BC and side AB is transversal, angle A plus angle B equals 180 degrees. Substituting angle A equals 90, we get angle B equals 90. Now, by the opposite angle property, angle C equals angle A which is 90 and angle D equals angle B which is 90. So, every angle of a rectangle is 90 degrees. That's why doors and tiles fit so snugly. All right angles. No gaps, no overlaps. Time for something trickier. The diagonals of a rhombus. Theorem says they are perpendicular. Take rhombus ABCD where all sides are equal. The diagonals AC and BD intersect at O. In triangles AOD and COD, we have OA equals OC, side AD equals side CD, and OD is common. By side-side-side congruence, the two triangles are equal. So, angle AOD equals angle COD. But these two are a linear pair, adding to 180 degrees. So each must be 90. Hence, the diagonals of a rhombus cross at right angles. Just think of the diamond shape in playing cards. Its diagonals meet at perfect 90 degrees every time. So, let's wrap up our story of parallelograms. A diagonal splits it into two congruent triangles. Opposite sides are equal, opposite angles are equal, and both results have converses. Diagonals bisect each other, and that converse works too. From these, special quadrilaterals like rectangles, rhombuses, and squares inherit even stronger properties. And every proof leaned on triangle congruence and the magic of parallel lines. So next time you see tiles on the floor, windows, or a chessboard, you'll smile because you now know the hidden mathematical DNA, the properties of a parallelogram. In the next video, we'll move on to the midpoint theorem, which beautifully connects triangles and parallelograms. Until then, keep exploring, keep practicing, and keep enjoying mathematics.